that's the first question. Well, then I guess we're done. Nice seeing y'all. See you tomorrow morning. Yes?
Well, let me get it really quick. It has to do, the evidence for dark matter from the rotation curves with spiral galaxies and the O historical connection to this.
Yep. What, you weren't there that day?
No, I just forgot.
You just forgot what I said. Okay. So, let's see, what chapter is that? It's 23, right? Yeah. So, if we measure Doppler shifts of stars or gas clouds in spiral galaxies, we can plot a rotation curve. We can measure for a rotating spiral galaxy. They all rotate because otherwise everything would fall into the center. There's a spiral galaxy, it's rotating. From our view here, this side would be moving away from us, and so spectral lines from stars or gas clouds would be red shifted on that side. They'd be blue shifted on the other side. And so measuring the Doppler shifts lets you calculate how fast things are moving at various radii away from the center of the galaxy. And in contrast to what we see for our solar system, where the further out planets are moving slower in their orbits. Their speed in their orbits isn't as fast. And that's a signature of the fact that in the solar system, the mass is concentrated at the center. In the sun, in a galaxy, a spiral galaxy, what we find is rotation curves tend to be nearly flat. This is the rotation curve for our galaxy, even beyond the visible disk of the galaxy. If you look at spectral lines from hydrogen beyond the visible disk of the galaxy, you still find that things are pretty much moving at constant speeds as you move away from the center of the galaxy. And that's telling us that there's a lot of mass there that we're not seeing that is responsible for the fact that things are moving that fast. If all the mass that we could see was all the mass that there was, then we would see speed falling off with distance away from the center. And the oval connection to that is that Vera Rubin used the Perkins telescope, not at Perkins, it was in Arizona, like it is still now when she was using it, but she used our telescope to study the Andromeda galaxy in particular, and then she started studying other galaxies too, not all with just our telescope. But in other words, there's this famous paper that Vera Rubin and a collaborator produced, wherein she mentions that the 72-inch telescope of the Ohio State and Ohio Wesleyan University was used to gather that data. So that's the oval connection. Any other questions about that? Okay, and somebody ask another question. Well, I'll just start bringing up random presentations so that they'll be ready when somebody asks a question that has something to do with it. You guys just all shy today? Or you studied so much you have no questions, you just wanted to see if somebody else has questions? Okay, seriously, somebody have a quick yes.
What exactly about the scientific method do you need to be familiar with? Because I remember there being like an essay question on the first example.
Yeah, so I wouldn't ask you an essay question, but like, for example, in the Mastering Astronomy, there were some examples of where they would ask you questions and you'd have to pick one. So you can ask multiple choice questions about that. Like, which of these is consistent with the hallmarks of science? Which of these is not consistent with the hallmarks of science? So, the outline of the scientific method, that you get taught from elementary school, basically, hypothesis, you test the hypothesis, and if you don't confirm it, you need to reformulate the hypothesis or completely chuck it out. Or if you confirm it, well, you run more tests and become more and more confident of it. And then there's those hallmarks of science figures of the book know what those hallmarks of science are. It's also in one of the presentations. Yes?
I'm confused on the difference between dark energy and dark matter.
Confused on the difference between dark energy and dark matter? You're not alone on that. It's confusing because unfortunately we call them both dark something, right? And so that kind of makes it confusing. But really, it's not too hard to keep them straight if you don't concentrate on the dark part and concentrate on one of them is called matter and the other is called energy. So the dark matter is the stuff that makes spiral galaxies have flat rotation curves. It's extra mass that we don't see associated with galaxies, associated with clusters of galaxies. Clusters of galaxies, when we measure the speeds of the galaxies in clusters of galaxies, they're moving fast enough that if all the matter that we could see in terms of stars and gas and dust was all the matter that there was, they'd fly apart on a time scale much shorter than the age of the universe. And yet there are still clusters and superclusters of galaxies being held together by gravity. So we infer from that there's a lot more mass there than meets the eye. Anybody remember what's the acronym for what we think that, we don't know it yet because we haven't seen it, we haven't detected it yet, but what do we call the stuff that we think the dark matter is mostly made of? WIMPs, yes, weakly interacting massive particles, right? Particles, so that right there says, oh, matter is what we're talking about there. So dark matter is, we think, a form of exotic matter that we don't yet know what it is, although we suspect it's a type of elementary particle that we haven't seen yet, but whose properties probably are that those particles interact via gravity and via the weak nuclear force and not the strong force and not the electromagnetic force. Dark energy, we think, is an energy associated with empty space itself, such that every cubic meter of empty space in the universe, and even cubic meters of space that has stuff in them, that space itself has an energy associated with it. That's the dark energy. We don't know what that energy is. We don't know what it is. So we're in the dark about it, hence dark energy. Dark energy is what is responsible for a kind of anti-gravity effect, so to speak. In other words, if you plug into the equations of general relativity and energy associated with space itself, you find that that would cause the expansion of the universe to speed up as a result of that. And so the dark energy is what is making galaxies move faster and faster away from one another over time, instead of what we used to think before we discovered otherwise using type 1a supernovae. We used to think a given galaxy which is moving away from us due to the expansion of the universe today would, if we came back in a billion years, be seen to be moving slower than it is now. Instead, what we've inferred is no, it would be moving faster in a billion years than it is now. Everything is, all the distant galaxies are slowly moving faster and faster away from us, and that would be explainable by the dark energy. So that's the difference between them. Any further questions about that?
Oh, no,
Yeah, okay.
that's fine.
Any further questions? I always try to remember to ask for, anybody have more questions about that, and then we move on to the next thing. Yes?
So where does baryonic matter come
So baryonic matter is quote-unquote ordinary matter. In other words, the stuff that stars, planets, people are made of. Baryons are, strictly speaking, they're particles that have 3 quarks in them. Protons and neutrons are baryons. But we call ourselves and the stuff that makes up stars and so forth baryonic matter because essentially it's protons and nucleons and nuclei, baryons and nuclei orbited by electrons. Electrons themselves are not baryons, but the matter whose mass is dominated by protons and neutrons, like our mass is, we call that baryonic matter. So baryonic matter is about 5% of the universe, the stuff that we can readily see more so. And the dark matter is the matter that isn't baryonic matter. is what it comes down to. It's kind of funny to say that baryonic matter is the ordinary matter when it seems to be the stuff that is not the most common kind of matter, but still, it's the stuff that makes us up, and so we tend to think of it as quote-unquote ordinary matter. Yes?
Can you talk a bit more about like singularity, event horizon, and the Schwarzschild radius?
Singularity, event horizon, and Schwarzschild radius. Yes. Yeah. Here in America, we tend to say Schwarzschild or whatever, but it's really more, like Schwarzschild, or something like that. But anyway, but yeah, Schwarzschild radius. It's fine. It's fine. So yeah, black holes actually, according to general relativity, have a relatively simple structure. They are actually not particularly complicated things. Now, if you throw in quantum mechanics, it could be much more complicated than that. But in terms of, despite the video I showed where Phil Platt was, I just want to be sure this is actually recording because it would be terrible if I came back later and discovered that the audience at home didn't have anything to watch. But anyway, despite him saying, oh, the equations are monster difficult and all that, actually, no, they're actually not, it turns out, for a classical general relativistic black hole. The structure of a non-rotating black hole is simply that there is a singularity at the center where all the mass would be concentrated. Does a singularity actually exist? Maybe not. Maybe quantum mechanics says you really can't do that. But nevertheless, the idea would be the singularity is a single point that has all the mass of the black hole in it. So it's infinite density because it's got zero volume. It's got mass divided by zero volume would be infinite density. So there's a point at the center called the singularity. There is a spherical surface surrounding it. Not a surface that has anything there, just a mathematical surface in space surrounding it, spherical in shape, called the event horizon. And the event horizon is where you'd have to go the speed of light in order to escape from the black hole. The escape velocity is equal to the speed of light at the event horizon. It's less than the speed of light outside the event horizon. So as long as you don't fall through the event horizon, if you had powerful enough rockets, you could get yourself out of the vicinity of the black hole. But once you're at the event horizon, you're at the surface of no return. No rocket would be powerful enough to get you away from it because no rocket can get you going the speed of light, and you'd have to go the speed of light in order to get away from the black hole at the singularity. I'm sorry, that's true. At the event horizon is what I meant to say just there, at the event horizon. So anything which is inside the event horizon is cut off from the rest of the universe. It can never get out. And the quote-unquote radius of the event horizon is what we call the Schwarzschild radius. Now this makes it look like it's literally the distance from the event horizon to the singularity. The curvature of space-time is so extreme in a black hole that that's really not the correct way to look at it. We call the Schwarzschild radius the radius of the event horizon, but what it really is that, and I'm not going to worry too much about you knowing this distinction particularly, but what it really is the thing that you square and multiply by 4 pi in order to get the area of the event horizon. The actual definition is that the area of the event horizon is 4 pi times the Schwarzschild radius squared, because the area of a sphere in general is 4 pi times its radius squared, except because of the curvature of space, you really can't think of this as a simple radius that's a distance from the singularity, is the idea. And that's pretty much what it comes down to. You got the singularity at the center where all the mass is, the event horizon, which divides the universe basically outside the black hole from anything that can happen inside the event horizon, and the Schwarzschild radius is quote-unquote the radius of the event horizon. Any questions about that? Okay. Yes?
Can you go over where it says to like understand the concepts of gravitational equilibrium and energy balance as applied to the sun and other stars?
Yeah, so a star, any stable, normal star is in a state of balance between essentially two forces. So those forces are gravity and pressure. So which chapter is that? What am I looking for?
14.
14, okay, yeah. So gravity, if it were unchecked, if there was nothing balancing it, then gravity would pull all the material in the star inwards. It would be collapsing if all you had was gravity. But pressure pushes outwards. So in any given layer in the star, the inward pull of gravity is balanced by the outward push of pressure, is what it comes down to. So that's what we mean by gravitational equilibrium, is that everywhere within the star, the inward pull of gravity is in balance with the outward push of pressure so that the star is stable. It neither expands nor contracts because those forces are in balance. The analogy is this stack of acrobats. That explains the idea that the pressure keeps getting bigger and bigger as you go deeper inside the star, and that's simply because there is more and more weight above it that has to be held up by that pressure. So with these acrobats, I mean, which of these guys has the toughest job? And you know, who needs to be the strongest? The guy on the top, the middle, or the bottom in terms of holding up weight? Guy on the bottom. Because the guy on the bottom has to hold up the weight of the two guys above him. The guy in the middle is got to hold up the weight of the one guy above him. Guy on top, well, I mean, I guess he's got to do this, which can be kind of difficult, but still, he's not holding anybody up. And similarly, the pressure increases as you go towards the core of the star because there's more and more material above it that has to be held up by that pressure. It's the same reason, that's exactly why air pressure is higher at sea level than it is on a mountaintop, because there's more air that sea level air has to hold up above it. It's also the reason why the deeper you go in the ocean, the higher the pressure gets, because there's more and more water above you that has to be held up by the pressure at any given depth as you go deeper down into the ocean. Yes?
Can we discuss how the age of a star cluster is determined from the location of the turn-off point?
Yeah, how is the age of a star cluster determined from the location of the turn-off point? So which chapter is that? What are we in here?
15.
15, okay. So, the idea is, one crucial piece is that stars are born in groups. So, stars, a big cloud of gas and dust collapses and forms multiple stars at the same time. So stars are like puppies, they're born in litters, so to speak, except that there's many more stars in a litter than there are puppies in a litter. And then the thing is, what do we know about how long a star lives versus its mass? So a more massive star has more fuel, it's got more hydrogen it's going to go through. Does that mean it lives longer, having more fuel to burn? No, it's the opposite. It actually lives shorter. Why?
Just the rate it burns.
Because the rate it burns its gas, so to speak, actually the hydrogen fuel, the rate at which it's fusing the hydrogen and helium, is so much greater for a more massive star. There more than makes up for the fact that it's got extra fuel. So the more massive a star is, the shorter the time it spends on the main sequence because it burns through its fuel faster than a less massive star does. So the idea is that when the cluster is young, you got stars of all masses along the main sequence. And they're all born at the same time, so they're all babies on the main sequence. So here's the what's so-called zero-age main sequence, stars that just got onto the main sequence. I'm simplifying because the lowest mass stars take extra time to collapse and reach the main sequence, but let's leave that aside. So here's a bunch of stars all on the main sequence. Which ones are going to run out of fuel first? The ones up here or the ones down here? The ones up there, because those are the more massive, hot O and B stars that are living fast and are going to die young. So you come back in 4 million years, and the most massive stars have already run out of central fuel and started turning into, in that case, supergiants. Whereas the less massive stars are still happily fusing hydrogen in their cores on the main sequence. You come back in 10 million years, and now some of these stars that were on the main sequence still when the cluster was 4 million years old, now they've run out of their fuel and left the main sequence. Come back in 100 million years, right when the cluster is 10 million years old, a 10 solar mass star is not done with its central hydrogen supply. But after 100 million years, it is. There are no longer any 10 solar mass stars on the main sequence because they've all used their fuel. And so on and so forth. The point is that the older the cluster is, the less and less massive stars are that have used up all their fuel. And the key, then, to figuring out how old the cluster is from the so-called turnoff point is, okay, in this case, for example, here's this cluster that's 1 billion years old. Here's its turnoff point right here. The turnoff point is, you walk your finger along the main sequence, and when it goes like that, when it starts peeling away from the main sequence, that's the turnoff point. We have computer models that can say, okay, for a star, I look at the turnoff point and I say, okay, that star right there, what's its surface temperature, based on that, what's its mass and so forth. For a star of that spectral type, remember the spectral type is correlated with surface temperature. For a star of that spectral type, computer models tell us how long that kind of star spends on the main sequence. In this case, our computer models would be telling us that stars on this part of the main sequence spend 1 billion years there before they start becoming red giants. And so that's how you would date the cluster. Where the turnoff point is tells you the age of the cluster. The age of the cluster is the main sequence lifetime of stars at the turnoff point, because those stars are just now ending their main sequence lifetime. So as a cluster ages, the turnoff point gets lower and lower down on the main sequence, and so there's a distinct correlation between how old the cluster is and where its turnoff point is. So for example, okay, help me out here. Let's see, the spectral sequence, it's O, B, A, F, G, K, M. What if I had 2 clusters, and for one of those clusters, turnoff point stars were spectral type A, and for another one of those clusters, turnoff point stars were spectral type K. What lives longer, an A star or a K star? K star. So which cluster is older, the one where A stars are just starting to leave the main sequence, or the one where K stars are just starting to leave the main sequence? The K star one, right. So knowing what stars are just now leaving the main sequence tells you the age of the cluster is how long it takes those stars to leave the main sequence. Those are precisely the stars at the turnoff point. The turnoff point is where stars are just starting to leave the main sequence, is the idea there. Okay, any questions about that? That is years of experience have taught me that that's one of the things that students find hardest to understand, is this idea of turnoff points and finding the age of a cluster from turnoff points and all that. So if you've got any questions about that, let me know, because like I say, I just know that's one of the things that people have trouble with. Yes?
How does it vary in terms of globular clusters and nodal clusters?
So when we look at globular clusters, we systematically see that their turnoff points are much lower down on the HR diagram, on the main sequence, such that globular clusters based on that, almost all of them are older than 10 billion years old, based on where their turnoff points are. For open clusters, they're all over the map in terms of where the turnoff point is. So for open clusters, they therefore have a range of ages, whereas globular clusters pretty much are all old. So based on that, are there any globular clusters forming now? If they're all, like almost all, 10 billion or more years old, how often are globular clusters forming today? They're not, because if they were, we would see young globular clusters, much younger than that. So apparently globular clusters, there was a time when globular clusters were being formed, and that was a long time ago. There might be some globular clusters forming now, but that's few and far between. Open clusters, we see a full range of ages. So are open clusters still being born? Yes, they are. Think of a population of people. So if you went to a country and everybody in that country was 65 and older, how's their birth rate going in that country? Nobody has kids in that country. If you go to a country and you go into the park and there's people of all ages, how's their birth rate going? Why, those folks have kids. So globular clusters are not being born anymore. Open clusters are still being born based on that.
You said 10 billion, right?
Yeah, about 10 billion or more, yeah. Yeah, globular clusters are being 10 billion or more years old. They're a significant fraction of the age of the universe, which is about 14 billion years, 13.8 billion years. So globular clusters were mostly born when the universe was still pretty young. A spring chicken, as these things go. Yes.
Can you explain the inflationary hypothesis a
Mhm.
bit more? I don't really understand.
Yeah, so the inflationary hypothesis. So the idea is that, yeah, that shows, it's chapter 22, is that right?
Yeah.
That's in that part of the guide, great. Okay. So there are a number of difficulties for cosmology that would be hard to explain without the idea of inflation. So one of them is that to extremely high precision, the geometry of the universe appears to be flat. So depending on how much mass and energy there were on average per unit volume in the universe, it could have one of three possible shapes if you assume that the universe is similar from place to place within it on large scales. It could be flat, and these are just analogies because our universe has 3 dimensions of space. It might have more, but they would be wrapped up in very small sizes, so I don't want to go there. So basically, at least macroscopically speaking, the universe is 3-dimensional, and all these surfaces are 2-dimensional. So the reality is something that our brains can't picture, except for the flat case. But in other words, it's possible to construct a 3-dimensional sphere in the sense that the quote-unquote surface of the sphere is in 3 dimensions instead of 2-dimensional, like the kind of spheres we can picture. So there's three possible geometries: flat, spherical, or saddle-shaped, depending on the overall density of matter and energy in the universe. There's a value called the critical density, which corresponds to about the equivalent of like 5, the mass and energy equivalent of 5 or so hydrogen atoms per cubic meter in the universe would be the critical density, which would make it flat in geometry. More than that would make it spherical in shape. It would cause space-time curvature that would make it spherical in shape. Less than that would make the universe saddle-shaped. That comes out in general relativity. So it shouldn't be obvious to you. It's just the way that you have to know general relativity to see where that comes from. Well, in principle, you could imagine that the density could have been anything. And flat is a very special case. It has to have just the right value in order to make it flat. And yet, our observations indicate that the universe is flat, and that's hard to explain. Why is the universe so special that it's flat, that the density is flat? And inflation can explain that. So inflation would be a very early on, when the universe is like 10 to the minus 30 something seconds old, 10 to the minus 36, 10 to the minus 34 seconds old, something like that. if there is a really super rapid expansion of the universe that starts suddenly and stops suddenly, then that can explain why the universe is flat now. And the idea is that before inflation, the universe could be very highly curved. But think of like a balloon. If you have a small little balloon, the surface is pretty strongly curved, and if you were an ant crawling around on that balloon, you could pretty easily tell you were crawling around on a smooth surface, on a curved surface. I mean. Now imagine, any real balloon would pop, but imagine taking that balloon and blowing it up so that it's the size of the Earth. Okay, this is super rubber. Could an ant crawling around on the newly super much larger balloon tell that it wasn't flat anymore? No, just like here, you know, when we crawl around on the surface of the Earth, is it obvious to you that Earth is curved? It is, by the way. The flat earthers are full of crap, but it is curved. But it looks awfully flat to us because the radius of curvature is very large compared to the area on the Earth's surface that we're able to see. Earth's radius is way bigger than the area on Earth's surface we're able to see, and that makes a curved surface look flat to us. And the idea would be, similarly, if you blow up the size of the universe tremendously via inflation, then afterwards, the part of the universe that we can see looks very flat because we're only seeing such a tiny portion of the entire universe, and it looks flat to us, similar to the way that a small part of Earth's surface looks flat to an ant. So inflation produces, in that sense, a natural explanation of why the universe is so flat. It started out very highly curved, but inflation would take any highly curved universe and make it almost flat for the part that you can see by the time you were done. So that's one thing that inflation does. Another thing that inflation does is solve what's called the horizon problem. So you remember from reading in the book, I hope, that the horizon refers to the distance in the universe out to which we could, even in principle, be able to see. Anything beyond the horizon is such that even if the universe had been transparent from the time of the Big Bang, a photon emitted from something which is beyond our so-called cosmological horizon would not have had time to have reached us since the Big Bang. And that means that we could never have interacted with anything that's beyond the cosmological horizon. And yet, when we look at the cosmic microwave background radiation, it's almost exactly the same temperature no matter what direction we look in. And in particular, and it actually doesn't even have to be this far apart on the sky, but if you look at the cosmic background radiation on opposite sides of the sky, it's essentially the same temperature on opposite sides of the sky. And yet you can show that if there had never been inflation, those regions would never have been able to be in contact with one another ever since the Big Bang. They would never have been, quote unquote, talking to one another, exchanging energy or particles with one another ever since the Big Bang. They would never have done so. So how did they manage to be the same temperature? Because things get to be the same temperature by interacting with one another. And inflation would solve that because the idea would be, here's these points on the cosmic microwave background that we're seeing that are the same temperature today, and without inflation, we would have this problem that this region A here that we're seeing today on one side of the sky could only have talked to, interacted with parts of the universe kind of in this region right here on this simplified picture. And this blob on the other side of the sky could only have talked to receive signals from this part of the universe, and those parts of the universe had never seen or heard from one another, talked to one another, so they wouldn't know that they're supposed to be the same temperature. The idea with inflation is, before inflation, those 2 points were close enough to be exchanging particles and energy with one another, so they would come to the same temperature. Then inflation rapidly moves them much farther apart. And so because they were in contact with one another before inflation moved them so far apart from one another, they were able to come to equilibrium, come to the same temperature before inflation, and then after inflation, they look like they had never talked to one another, but that would only be if there had never been inflation, is what it comes down to. And so inflation solves the mystery of why is the universe flat. It solves the mystery of why is the cosmic background radiation the same temperature in every direction to a very high precision. And I forget, did I say on there something else you should understand about inflation? I don't remember. Yeah. Yeah, it's always, when I get to cosmology, that you run into the problem of, you know, it's the end of the semester, there's only a limited amount of time to cover it, and there's a lot of difficult, kind of strange concepts that are involved, and so I always feel like it's hard to do it justice. Which again, you know, I put in the advertisement. If you want to know more, if you took Astronomy 260 next year, then you learn a lot more of the details about how all this works. But yeah, so anyway. Yes.
What direction does the acceleration vector point in uniform circular?
What direction does the acceleration vector point in uniform circular motion? Okay, so I'll go back to what I did in class. Imagine that you pick up your little sister or little brother and spin them around. So you hang on to them, spin them around. They're moving in a circle. Are they accelerating? They're moving at constant speed, but are they accelerating? No, so remember that everyday language is that acceleration is a change in speed, but in physics, acceleration is a change in velocity. And velocity includes both how fast you're going and what else? Direction. So I'll ask the question again. Little sister is moving at constant speed. Is she moving at constant velocity? No, because the direction she's moving is continuously changing as she moves in a circle around you. So she's accelerating. The acceleration is in the same direction as the force which is causing it, and our intuition can tell us what direction that force is in by asking yourself, as I am swinging little sister around, what am I doing? Am I pushing out on her or pulling in on her to keep her moving in a circle? I'm pulling in on her. I got to pull in on her to keep her moving in that circle. So the force on little sister is in towards me. So the centripetal force is towards the center of the circle, and that means that the centripetal acceleration, center-directed acceleration, it's towards the center of the circle. So in uniform circular motion, both the force and the acceleration are towards the center of the circle. We did that too. You do it with like a ball on a string. If you take a ball on a string and whirl it around above your head, the ball is moving in uniform circular motion, and in that case, the string is pulling